This is part 2 of the notes video for AP Calculus on the topic of local and relative extrema and the first derivative test, along with increasing and decreasing intervals. So when my pen ran out of battery, I was right here on this problem here. So we'll pick up where we left off on the part 1 video. So we're using the product rule overall, and we had just put the first function as it is, and now we're about to take the derivative of the second one. So first you would use the power rule, bring the 2 out in front. And then it's x minus 5 now to the first power. And technically it's a chain rule, but notice the derivative of the inside derivative x minus 5 is just 1. So in this case, the chain rule doesn't really affect it because you would just multiply by 1. All right, and so now to see where this is 0 undefined, notice there's no negative exponents or denominators, so you won't have any undefined critical numbers that make the function derivative undefined. So you want to see what makes it equal to 0. And to solve that, what you can do is factor out the greatest common factor, the GCF. So here's the first term, and here's the second term. And here what they have in common is an x minus 5 to the lower exponent is 1, so just 1x minus 5. You can take out as a GCF. And then what we have left, what's left of the first term is this 3. And since there is x minus 5 squared, we'd have 1x minus 5 left as well. And then plus what's left of the second term, we've got this 2 here that's still left that we didn't factor out, along with the 3x plus 1. Then oftentimes when you take out the GCF, there's some simplifying to do with what's left, and that's the case here. So to make this simpler, so we can see the other critical numbers, you can first get rid of these inner parentheses here by distributing out the 3. So 3 times x is 3x. 3 times negative 5, negative 15. And then plus, and then here you can distribute out the 2. 2 times 3x is 6x. And 2 times 1 gives you 2. And then we've got some like terms we can combine. That's 3x and 6x combined to give you 9x. Negative 15 plus 2 is negative 13. Occasionally there might be another GCF you could factor out at this point, but in this case with 9 and 13 there isn't. So now we've got it in factored form. One of these has to be 0 to make the derivative 0. So if you set x minus 5 equal to 0, you get x equals 5. And if you set 9x minus 13 equal to 0, you add the 13 divided by 9. So you get x equals 13 over 9. So those are your two critical numbers that we'll put on the number line. And again, always label your number line. In this case, g prime of x. And 13 over 9 is the same as 9 goes into 13 one time, and there's 4 left over, so that's 1 4/9. So you can see that's less than 5. So we've got 13 over 9 goes first, and 5 right here. And both of those make the derivative equal to 0. And here we could test something less than 13 over 9. You could test 1, or you could test 0, is probably easier. So if you test 0, 0 minus 5, and the factor form again is the easiest form to test in as opposed to one of these forms to see if it's positive or negative. 0 minus 5 is negative. 0 times 9, that's 0 minus 13, that's negative. Negative times a negative is positive. In between 13 over 9, remember that's 1 4/9 and 5. You could choose 2, 3, or 4. Let's say we choose 2. 2 minus 5 is negative. 2 times 9 is 18. Minus 13, that's positive. So negative times a positive is negative. And something greater than 5, like 6. 6 minus 5 is positive. 6 times 9 is 54. Minus 13, that's positive. Positive times a positive is positive. So in this case, remember, we were just looking for the x coordinates of the local mins and maxes and then to justify our answer. So what this shows us about g of x, the original function, is that since the first derivative changes from positive to negative here, it goes increasing to decreasing. That's going to be a relative max. And since the first derivative here changes at 5 from negative to positive, it's going to go from decreasing to increasing. That's a relative minimum. And now we just have to write those down and justify our answers. So we can say G has a, now here it calls them local mins and maxes, same thing as relative, either way. I'll just use the same wording that's in the question. So it has a local maximum at x equals 13 over 9. And then the way you justify it would be since you have to refer to the first derivative. In this case, it's g prime of x. Since g prime of x changes from, and we're moving from left to right, so from positive to negative at x equals, you have to specify where that change happens, is right at x equals 13 over 9. And then we can justify our local minimum, g as a local minimum at x equals 5. And then to justify it since, very similar, except this time it's since the derivative g prime of x changes from negative to positive at x equals 5. So that's how we identify and justify our local minimums and maximums. Notice you could also figure out the increase and decrease intervals, it just wasn't asking for it in the problem, which is why I didn't write it down there. All right, finally let's take a look at two special types of functions, a piecewise function and then a trig function, and how we find the same information on those, relative mins and maxes, increase and decrease intervals. So for piecewise functions, the first thing to be aware of that's different is the breakpoints of the piecewise functions are always critical numbers. The reason why is because on a piecewise function, when you have the breakpoints, it switches between one equation, part of the equation, and another. So at that x value where it switches, it could easily change from increasing to decreasing or positive. The first derivative could change from positive because it's totally switching equations. So they have to be under number line for sure. And then what we also need to figure out is to determine if the function is continuous or not at each breakpoint. And we'll do this just like we've done before by comparing the left and right hand limits to see if they're equal or not. And we'll see why that's important in just a little bit. And then we'll have to take the derivative and find the critical numbers of each piece and only use critical numbers in the domain of the corresponding piece. So we'll see what that looks like on our example problem. And when testing between intervals between critical numbers, be sure to use the piece of the function that corresponds to the interval you're testing. So these ask for the increase and decrease intervals and define the x coordinates of all the local extrema, means local mins and maxes, and identify each as a local min or max. But it doesn't ask you to justify it, so we don't have to here. If we did, we justify it like we did the other ones. So the first thing to do, in this case, the breakpoints are wherever this function splits into different pieces. So in this case, -1 and 3. Those are definitely going to be on the number line. Those are definitely critical numbers for sure. But what we have to figure out is if the function's continuous or not there. So the way we do that is find the limit as x approaches -1 from the left and compare it to the limit as x approaches -1 from the right. So -1 from the left, we use this top piece here and substitute -1. So that's -1 plus 3 squared. That's 2, whoops. That equals 2 squared, which is 4. So there's our left-hand limit. And we'll compare that with the limit as x approaches -1 from the right. So that'll be -2 times -1 plus 2 gives you 2 plus 2, which is 4. So since they're equal, that means the general limit would be 4, but it also, in this case, means f is continuous at that breakpoint at x equals -1. So let's do the same thing for the other breakpoint, and then we'll talk about why it's important whether the function is continuous or not. So our other breakpoint, you can see, is positive 3. So let's do the same thing, see if it's continuous or not at 3. So the limit as x approaches 3 from the left Well, that would be this middle piece here, so negative 2 times 3 plus 2. That's negative 6 plus 2 gives you negative 4. And we'll compare that with the limit as x approaches 3 from the right. That uses this bottom piece, so negative 3 cubed plus 12 times 3 squared. So 3 cubed is 27, the negative just stays out in front. 3 squared is 9 times 12 is 108. And 108 minus 27 is 81. So in this case, they're not even close. Negative 4 versus 81, they don't meet up. Left and right limits, so f is not continuous at x equals 3. So the importance of that is, remember, these definitely have to be critical numbers. They're going to be on our number line no matter what, because the function changes to a different part of the equation. But if it's continuous, that means this could potentially, at negative 1, could potentially be a relative min or max, because it's connected. But if it's not continuous, no matter what we find on the number line, there's no way we can have a relative minimum or relative maximum at 3, because the function isn't even connected. Okay? All right, so now what we do is we find the derivative of each piece. So f prime of x equals, so the derivative of the first piece would just be 2 using the power rule times x plus 3 to the first. And then using the chain rule, the derivative inside is just 1, so that doesn't affect it. And that applies for x is less than negative 1. Then the derivative of the second piece is just negative 2, and that applies for, and notice I'm going to drop off the equal to sign here, and we'll see if the function is actually differentiable at negative 1 or not. It was continuous, so it might be differentiable, and you can check really quickly if it is or not. It doesn't really affect our answers to this question, but to see if that derivative exists, to see if it's a corner or not. If you plug in negative 1 into the derivative here, you get negative 1 plus 3 is 2 times 2 is 4. And notice when you try to plug in negative 1 here, you just get negative 2. So 4 versus negative 2, those are different. So it's a corner there. It's connected, but it's a corner, so it would not be differentiable, so you would take off the equal sign. If these had been equal, then it would be a nice smooth curve, and we would leave the equal to sign on. But again, it doesn't affect our answers here, just a small technicality here. All right, and then the derivative of the last piece is negative 3x squared plus 24x, and that applies 4. Now here, because the function is not even continuous there, it's definitely not differentiable, so the derivative definitely will not exist, so I'll take off the equal to sign at 3. And now we just have to find the critical numbers of each of these. Notice none of them have a denominator or negative exponent, so we don't have to worry about the undefined, just where it equals 0. So let's set each of these equal to 0 to find our critical numbers. So 2 can't be 0, so if you set x plus 3 equals 0, we get x equals negative 3. And then what we have to check here, what this is standing right here, remember to only use critical numbers that are in the domain of the corresponding piece. So we have to check, whoops, negative 3, is that less than negative 1 here? It is, so we would use negative 3, so that is a critical number, along with our breakpoints. Now, look at the middle piece. Negative 2 will never be 0. There's no x's in there, so that doesn't give us any critical numbers. And then the last piece, negative 3x squared plus 24x, if we set that equal to 0, you can factor out a 3, and it's actually easier if you factor out a negative 3 along with the x as a GCF, and then we're left with x minus 8. Since we took out a negative, it changes the sign. So one of these could be 0. If you set negative 3x equal to 0, you get x equals 0. If you set x minus 8 equals 0, you get x equals 8. But again, we have to check and see if these are in the domain of that piece. So if you check 0, is 0 greater than 3? It's not. So you would never plug 0 into this piece. 0 is in this interval, so you would actually use the middle piece. So because of that, 0 is actually not a critical number. A little arrow here. And I'll write it's because it's not in the interval. But 8 is greater than 3, so you would use 8 on this one, so 8 is a critical number. So we found two additional critical numbers, -3 and 8, along with the two that we had to put on there, the breakpoints, -1 and 3. So altogether, we're going to have 4 critical numbers when we draw our number 1. And again, label it f prime of x. All right, and let's put them in order. So the lowest out of these is -3, then -1, our breakpoint, then +3, our other breakpoint, and then +8. Now, -3 and 8, both of those made the derivative 0. And what's the important thing at these points is whether it's continuous or not. So the breakpoint. So -1, we'll just put it is continuous. And at 3, it's not continuous. All right, so now when we're testing, we just have to make sure we test in the correct piece. Again, based on the domain here. So here, if you test something less than -3, like -4, that fits in this interval. -4 plus 3, that's negative. Between -3 and -1, you could test -2, that's also in this interval. -2 plus 3 is positive. Between -3 and -1 and 3, you could test 0. 0 is in this interval, but when you try to plug in 0, there's no x's. It's always -2. So that one's always negative. Then here you could test something between 3 and 8, like 4. 4 is greater than 3, so you use this piece. You could try to test it in here, but it's easier to use the factored form. So if we use the factored form, 4 times -3 is negative. 4 minus 8 is negative. Negative times negative is positive. And here we could test 9. That's also in this interval, greater than 3. So if we test 9, 9 times -3 is negative. 9 minus 8 is positive. Negative times a positive is negative. So again, it doesn't always alternate back and forth, but this one happens to. So that's going to show us our increasing and decreasing intervals right there. So this shows us that f of x, the original function, when the derivative is negative, the slope is negative, that means it's decreasing. Positive means it's increasing. Back to negative, decreasing, positive, increasing, and negative, decreasing. So we can write down our increase and decrease intervals first. Say f is increasing. On -3 to -1, and then also from 3 to 8. And f is decreasing on -infinity to -3, and -1 to 3, and also 8 to infinity. And then finally, we have to write down which of these critical numbers are actually relative mins or maxes. So notice at -3 goes decreasing, increasing. The first derivative changes from negative to positive. So that's a relative minimum. At -1, changes from positive to negative, increasing to decreasing. And it's continuous. So because it's continuous, that is a relative maximum. And it switches. Now notice at 3, decreasing to increasing, that looks like a relative minimum. But because it's not continuous, it's neither. It's not even connected. And then 8, that goes increasing to decreasing. The first derivative changes from positive to negative. That's a relative max. So we have 2 relative maximums and 1 relative minimum. So we can say f has relative maximums at x equals -1 and x equals 8. And f has a relative minimum at x equals -3. And that answers all the questions that we were asked about this piecewise function. All right, last one let's take a look at here is a trig function. So same instructions here. So first let's just rewrite this cosine squared, what that really means. So this is still f of x. So it really means cosine of x squared. And then plus cosine of x. What's different about the trig functions, they're usually going to give you some interval it applies on. In this case, from 0 to 2 pi. Otherwise, because they keep repeating over and over again, you could oftentimes have an infinite number of increasing and decreasing intervals, an infinite number of relative minimums and maxes, so we just want to restrict it to just this interval. So let's find the derivative now. So notice on this one, we've got to use the chain rule. So first use the power rule, so it'd be 2 cosine x to the first. And then the derivative inside derivative cosine is negative sine. And then plus the derivative cosine by itself is negative sine. Normally I wouldn't put this plus sign here, but to make it easier to factor, because we want to see what our critical numbers are. Now, if I leave it in this form, you can see this is all multiplied together. That's our first term. Plus, there's our second term. So what we can take out as GCF is a sine x and also the negative. You don't have to take out the negative, but it does make it a little simpler if you do. So if we take out the negative sine x as our GCF, then let's see what we have left. So we've got 2 cosine x and plus, since we took out the negative, and then since we took everything out, you still need a 1 to hold the place there. So now to see what makes this 0, one of these has to be 0. So if you said negative sine x equal to 0, that's just like setting sine x equal to 0, because the negative opposite of 0 would still be 0. And then, or the 2 cosine x plus 1 could equal 0. So the negative here doesn't affect what makes it 0, but it will affect when we're testing in our intervals. So where sine is 0, we're looking for the angles between 0 and 2 pi. Well, if it's 0, we can't draw a triangle, so it's got to be right on the axis here. So let's see if we can find where that is. Well, sine represents the y-coordinate. So notice the y-coordinate is 0. Right here, it's 1, 0, and right here on our unit circle, negative 1, 0. So the angles that fit that between 0 and 2 pi, 0, pi, and 2 pi. So those are our critical numbers here. These three will make sine 0. And then to solve this one, we've just got to isolate the cosine. So subtract the 1 and divide by 2. So we're looking for where cosine is negative 1/2. And to figure this one out, this one we do draw a triangle. Remember, cosine SOHCAHTOA. Cosine is the adjacent over the hypotenuse. So we have to draw our triangles here, where the adjacent would be negative 1 and the hypotenuse would be 2. So between 0 and 2 pi. So if you want the adjacent to be negative, it's got to be in the second or third quadrant. So we'd have to draw these triangles over here. So the adjacent is negative 1, the hypotenuse is 2. And then we have to find what these angles are. So notice this is a 30, 60, 90 triangle. This is the 60 degrees, which is pi over 3. So to figure that out, this one's pi, which is the same as 3 pi over 3. So this is pi over 3 less than it. So that would be 2 pi over 3. And this is pi over 3 more than 3 pi over 3, so that would be 4 pi over 3. So that gives us our other two critical numbers. 2 pi over 3 and 4 pi over 3. So now we just have to put these all on the number line. But on this number line, we're only looking between 0 and 2 pi. Okay, and I'll label it f prime of x. And notice, in this case, 0 and 2 pi are already our endpoints. So we'll just have pi, 2 pi over 3, and 4 pi over 3. Let's put them in order. So going around a circle, starting at 0, the first one we hit is 2 pi over 3. And then the next one we hit is pi. And then 4 pi over 3. And then 2 pi. So all 5 of these make the derivative 0. And then the testing is a little trickier. You just have to find angles in between these that are ones we can test using our special triangles or using the points right on the axis. So I'm actually going to write down what we're testing so you can see it a little more easily. So between 0 and 2 pi over 3, we've got a lot of choices. You can use pi over 6, pi over 4, pi over 3, but pi over 2 is probably the easiest because you don't have to draw a triangle. So I'm going to test pi over 2. So right down here, I'm going to draw another unit circle here so we can show what we're testing. All right. So pi over 2, coordinates at that point are 0, 1. So we need the sine and the cosine. So sine is the y-coordinate 1, but that is multiplied by this negative here, so that's a negative 1. And cosine of pi over 2 is the x-coordinate 0, that wipes this out, so you get 0 plus 1 is positive. So negative times a positive is negative. Now between 2 pi over 3 and pi, that's a smaller interval there. So you could choose either 3 pi over 4 or 5 pi over 6 would be the two different ones you could choose. Either one is fine. Oh, notice I forgot to mention on this first interval, 0 would have been easy to test also, but I couldn't test it in this case because it was a critical number. It was 0. If it wasn't a critical number, I could have tested 0 in addition to pi over 2, either one. So on this one, let's go ahead and draw 5 pi over 6. So that's what we'll test here. And we need sine and cosine, so let's put in all the sides. So this is another 30, 60, 90 triangle. This time this is negative root 3, this is 1, and this is 2. So sine would be opposite over hypotenuse, so 1/2. But again, times this negative 1 would be negative. And then cosine would be negative root 3 over 2 adjacent over hypotenuse. So if we put that in here, for cosine, notice it's going to get multiplied by the 2. So the 2's are going to cancel out there. Whoops. And we'll be just left with negative square root of 3 plus 1. So square root of 3 is like about 1.7. So negative 1.7 plus 1, that's going to be negative there. So it will be a negative times a negative will be positive. Then we have to test something between pi over and 4 pi over 3. So here, since we already used 5 pi over 6, the easiest one to use would be 7 pi over 6. It's almost the same triangle. This is still negative root 3. This is still 2. The only difference is this is negative 1. So let's test 7 pi over 6. So for 7 pi over 6, sine would be negative 1 over 2. So that's negative 1/2, but then it's multiplied by this negative. Those negatives cancel out, making it positive there. And notice cosine is identical. So we still get the exact same thing, negative root 3 over 2. So the same thing's going to happen. The 2's will cancel. Negative root 3 plus 1 is negative. So it's a positive times a negative is negative. And then the last interval, again, I could use 2 pi if it wasn't a critical number, but in this case it is, so I'm just going to get 0 to test in the derivative. So another easy one between 4 pi over 3 and 2 pi would be 3 pi over 2. So let's test 3 pi over 2 here. Three pi over 2 is right down here. The coordinates at that point are 0 and -1. So sine is -1 times this negative out in front, again, makes it positive. And then cosine is 0. That wipes this out, gives you just 0 plus 1 is positive. So positive times a positive is positive. So now we can write down, this shows us that f of x is decreasing when this first derivative is negative, then increasing, decreasing, and back to increasing. So we can write down those intervals first. F is increasing on 2 pi over 3 to pi and 4 pi over 3 to not to infinity, but to 2 pi. Now in this case, I'm going to put a parentheses on 2 pi. But if it hadn't been a critical number and it was positive here, then I would actually put a bracket on it. In this case, though, you don't need it. And then f is decreasing on, again, normally if this wasn't a critical number, that means 0 would be negative. I would put a bracket on the 0 to show it is decreasing there, but since it's 0, you don't have to. It's just 0 to 2 pi over 3. And from pi to 4 pi over 3. And then finally, let's find our relative mins and maxes. So here the derivative changes from negative to positive. Notice it might switch at 0, but because we're only looking between 0 and 2 pi, we're not testing this interval, so we can't say based on this interval if this is a relative min or max, because we're only looking there. So here we've got a relative min. Goes from decreasing to increasing. At pi, it goes increasing to decreasing. The first derivative changes from positive to negative. That's a relative maximum. Then at 4 pi over 3, it goes from negative to positive, decreasing to increasing. That's another relative minimum. So we can say f has a relative maximum at x equals pi, and f has relative minimums at x equals 2 pi over 3 and x equals 4 pi over 3. And that's what I was asking for. And that concludes the notes for part 2 on the topic of relative minimums and maximums, which are the same as local mins and maxes, increasing, decreasing intervals, and we're using the first derivative test.